So today we're going to continue the discussion of game theory and its applications in AI. So I'm going to tell you about two really beautiful ideas. The idea of correlated equilibrium and the idea of Stackelberg games, which we'll see in the context of security games. And especially when we talk about Stackelberg and security games, we'll devote some time to thinking about the applications of these ideas in AI. Okay, so let's start by talking about correlated equilibrium. I want to jump straight into it, so hopefully you guys remember the notations and definition we use to talk about Nash equilibrium. Correlated equilibrium is a trickier concept. I think it's a really subtle concept, yet a really ingenious concept. It's one of the concepts that won Bob Uman the Nobel Prize in Economics. It's a really, really brilliant concept, as we'll see in the next few minutes. But again, a warning is it is somewhat subtle, so if you feel confused, that's pretty natural. Okay, so we're going to have just two players in this definition for simplicity, just to simplify the notations. And another entity that we have when we talk about the correlated equilibrium is a mediator, which sort of helps the players coordinate. So the mediator is going to choose a pair of strategies, S1, S2, for players 1 and 2, from a probability distribution P over the product space of the two strategy spaces. So basically, just choosing a strategy for player 1 and a strategy for player 2 according to a joint probability distribution. Okay? So this is really the crucial point and the place where the word correlated is coming from. The strategies of the two players are going to be correlated by the mediator. So it's not two independent mixed strategies like we had before. We're going to draw strategies from this joint distribution. Now the mediator reveals S1, the strategy of player 1, to player 1, and S2 to player 2. And the point I want to make is that when player 1 gets some advice, he's told by the mediator to play S1, he has some idea of what the mediator told player 2 to play. Okay? So what is that? We're asking, like player 1 is asking himself, what's the probability that the mediator told player 2 to play S2, given that I, player 1, was told to play S1? And remember that everybody knows P. Okay, so this probability distribution P is known to both players. What's unknown to each player is which strategy the mediator told the other player to play. Okay, but again, the point is, player 1 can deduce some information about what player 2 was told, given what he was told. So what's the probability that the mediator told player 2 to play S2, given that player 1 was told to play S1, which he knows? So it's just by definition, it's the probability of S1 and S2 divided by the probability of S1. Now notice that the probability of S1 and S2 is just P of S1, S2, according to this function P. And the probability of S1, we can just use the sum rule, so it's the sum over all S2 prime of P S1, S2. So this means that player 1, when he is told to play S1, he can compute the probability that the mediator told player 2 to play S2, given that he knows this probability distribution P. Okay? Is this point clear? We're going to look at we're going to practice this concept for a few slides, but so far does this look okay? Okay, so the idea we want to capture here is sort of the same idea as Nash equilibrium, but here it's a bit more subtle because the mediator is involved. So what we want to say is, player 1 is best off listening to the mediator, given that he knows that player 2 is listening to the mediator. And the same thing goes for player 2. So in order to say that, we again have to define this notion of best response. What does it mean for player 1 to be playing optimally, given this assumption about what player 2 is doing? So in this situation, we're going to say that player 1 is best responding if the following condition holds. So, what is this? This is the expected utility to player 1, given that he's playing S1 as he was told. And player 2, the probability that player 2 plays each strategy S2 we can compute it as before. So we just sum over all S2. We look at the probability that player 2 was told to play S2, given that player 1 was told to play S1. And then we look at the utility of S1 and S2. This is the expected utility to player 1 if he plays S1 as he was told. Now he could choose to play something else, S1 prime. And then his expected utility, the only thing that would change is his utility in every situation would depend on the pair S1 prime and S2. But the probabilities are exactly the same as before, right? Because he was still told to play S1. That gives him the information about what player 2 will do. He can choose to play something else, but that information about what player 2 is doing is the same. So the probability is, in terms of how probable it is for player 2 to play S2, given that I was told to play S1, that's the same. But now if I choose to play S1 prime instead, the utility would change to the utility for S1 prime and S2. Okay? So this is what it means for player 1 to be best responding by actually playing the strategy S1 as he was told. Now notice that this thing, the probability of S2 given S1, we can just rewrite it using what we had on the previous slide. So we can just say it's PS1 S2 divided by the probability of S1. Okay, so we can replace this by PS1 S2, and things will also be divided by the probability of S1, but that's going to be the same for all of the terms on both sides of the inequality. So if we just multiply by the probability of S1, we get this inequality. So I'm claiming that this inequality is equivalent to this inequality based on what we derived on the previous slide. Okay? So we can just replace the probability of S2 given S1 with the probability with P of S1 and S2. And then we say that P is a correlated equilibrium if both players are best responding, and more generally if all players are best responding. Okay? Demetrius?
Can you repeat why it's not probability of S2 given S1 prime?
Yes. Here. Right, so the reason is that what we're assuming is that player 2 is going to play according to the advice given to him by the mediator. So we're player 1, we were told to play S1, and we know that this was drawn from the joint probability distribution P. So player 2 was told to play something, based on the fact that we were told to play S1, or the mediator drew S1, S2, told us to play S1, and he told player 2 something that is correlated with that fact. Now the fact that I choose to play something else doesn't change what player 2 was told. It doesn't change like the draw of the mediator. Right? So the probability over the actions of player 2 is still the same, but I can change my utility by choosing to play a different strategy instead. Does that make sense? Yeah. Priya.
So just to clarify the last statement, so we're saying that there's a joint probability distribution. That probability distribution is the correlated equilibrium.
Yes,
So
yes.
Are we implying that every pair that we would draw from there would have this best response? Right?
Yes,
Okay.
yeah, exactly. So every time one player is being, when we draw a pair, one player is told to play some strategy, given the probability distribution it induces over the strategies of the other players, these conditions would hold. That's a good point, actually. Okay, that's an important clarification. So what I'm saying here is that every time one player is told, if P is a correlated equilibrium, every time a player is told to play some strategy, when we drew a pair of strategies from P, these conditions would hold. Okay? Okay, so let's look at an example, and hopefully this will become more intuitive. So the example is coming from a famous game. It's one of the paradigmatic games in game theory. It's called the game of chicken. I'm not going to show you this movie clip because we have a lot of stuff to cover today, but you can look at it online. So it's a scene from this movie Rebel Without a Cause, which is one of the famous examples of the game of chicken. Let me tell you about a slightly different variant than what you see in the scene. So the idea is it's like teenagers fighting for their honor. And so what they do is they drive two cars in one lane, like towards each other. And then they can basically choose to swerve, and then they basically chicken out, or they can choose to go straight. And if the other player doesn't swerve, there'll be a collision and they both die. So the strategies are either chicken, which is swerve, or dare, which is continue driving straight no matter what. And of course, if one of them chickens out and the other dares, the one who dared gets a lot of honor, and the one who chickened out loses his honor. And if they both dare, they die. And if they both chicken out, it's not that bad. So here's like a representation of this game as a normal form game. So like I said, the strategies are chicken and dare. Conveniently, it's a C and D, like cooperate and defect from the prisoner's dilemma. And, and the numbers sort of give one interpretation for this story that we just told. Okay, so let's, just for the purpose of reasoning about this example, let's define this notion of social welfare. More accurately, it's the utilitarian social welfare as the sum of utilities that two players get from an outcome. So for example, if they play dare, the social welfare will be 0. And if they play chicken, the social welfare will be 6, 3 plus 3. Now, in this game, there are two pure Nash equilibria, they're sort of very easy to spot, chicken, dare, and dare, chicken. So if you're daring, the other guy's chickening out, you're happy, of course. If the other guy is daring and you're chickening out, you don't want to switch to dare, otherwise you die. Now, another mixed Nash equilibrium in this game is when both players play 1/2, 1/2. Okay? And the way to see this is, let's take the point of view of player 1. And let's say that player 2 is sort of uniformly randomizing between chicken and dare. So if we play dare, we get 1/2 times 0 plus 1/2 times 4, which is 2. If we play chicken, we get 1/2 times 1 plus 1/2 times 3, which is again 2. So either way, we're sort of indifferent between these two options, given that the other player is uniformly randomizing between chicken and dare. But the thing is, if this happens, the social welfare, like if both players play 1/2, 1/2, we actually get dare with probability 1/4, and the social welfare is not that great. So we're going to have 1/4, 1/4, 1/4, 1/4. So the expected social welfare will be 5 plus 5 plus 6, that's 16, divided by 4, which is 4. Okay, so it's actually lower social welfare than if we have chicken and dare or dare and chicken. And intuitively, the reason is that we have significant probability on dare, which is a really bad outcome. And of course, on the other hand, the optimal social welfare here is when both play chicken, and then the social welfare is 6. Okay, so the Nash equilibria here are not that great in terms of social welfare. There's actually a large line of work in algorithmic game theory about the price of anarchy, which is how inefficient equilibria can be, but we won't talk about that at all. What I do want to show you is that with the correlated equilibrium, we can actually recover some of the loss that we had because of the Nash equilibria versus the social optimum. So let's look at the following distribution P over pairs of strategies. It gives DD probability 0. Player 1 playing dare, player 2 playing chicken, that's DC, probability 1/3, CD probability 1/3, and CC probability 1/3. So one thing to notice here is, let's first assume this is okay, this is an equilibrium. One thing to notice is that dare is never played. Okay, so we've sort of circumvented that problem. And notice that the social welfare, we're just playing this with probability 1/3, this with probability 1/3, and this with probability 1/3. So now the expected social welfare will be 16 divided by 3, which is higher than anything we had before. Okay, so that's good news. Now I want to convince you that this probability distribution is actually a correlated equilibrium, and hopefully this will give you the intuition for what's going on here. So let's take the point of view of player 1. Okay? And let's first assume that player 1 is told by the mediator to play dare. Now, there's only one, because this happens with probability 0, there's only one outcome, one pair where this actually can happen, which is the pair dare chicken, right? Which happens with probability 1/3. But the point is, given that we as player 1 were told to play dare, we know for sure that player 2 was told to play chicken, right? And the way to see this mathematically is the probability would be the probability of dare and chicken, which is 1/3, divided by the probability that we were told to dare, which is also 1/3, right? And then 1/3 divided by 1/3 is 1. So when we're told to dare, we know that player 2 is being told to chicken. And therefore, obviously, our best response is to dare. That's the best outcome for us. So the trickier thing is what happens when we're told to chicken. Right, this is sort of intuitively like you want to keep your honor. The mediator tells you should chicken. I mean, that sounds bad. So let's see why this is actually makes sense for player one to follow that advice. So if he's told to play chicken, we know that we're either in this outcome or in this outcome. Now notice that both of these are equally probable. So therefore, when we ask what's the probability that player two was told to dare, given that we were told to chicken, it's going to be 1/2. And when we ask what's the probability that player two was told to chicken, given that we were told to chicken, that's also going to be 1/2. And again, the way to see this is if you ask what's the probability of dare given that I was told to chicken, it's going to be 1/3 divided by the total probability that I was told to chicken, which is 2/3, that gives you 1/2. Okay? So given that we're told to chicken, the other player, we know there's probability 1/2 they played dare, probability 1/2 they were told to play chicken. And remember on the previous slide, we said when a player is randomizing uniformly at random, we are indifferent between, like the other player should be indifferent between chicken and dare. Okay? So we can do this calculation again, but we just did it. Right? So just, if we say player two is randomizing 1/2, 1/2, we get expected utility 2 for both dare and chicken, so we're indifferent. So, given that we were told to chicken, we know the other player is just randomizing uniformly at random, and therefore we might as well play chicken, like it's the same to us. Okay? So, intuitively, what's happening here, I think this is really a brilliant idea, so I really hope you see the intuition here, which is in Nash equilibrium, the problem we had, we sort of want to capture this idea that when one player is randomizing uniformly, it's, the other player can do whatever they want, it's going to be the same to them. The problem is that in Nash equilibrium, if both players sort of randomize uniformly, then, there's a chance that both of them will choose dare and they both die. Now here, this sort of captures the fact, captures this thing of like, if one guy is randomizing uniformly, the other can do whatever we want, it would be okay. But because we were able to correlate the randomness of the two players, we're able to avoid the situation where both of them play dare, and that sort of gives us higher weight on the socially good outcomes. Okay, so that's really sort of the intuition behind why we were able to do better. Matthew?
The example that you're giving makes sense with those particular values for each of the quadrants. But if, for instance, dare chicken or chicken dare, I personally would think that the difference between surviving and losing is greater than the difference between losing and winning.
Sure. I mean, I'm not making a general statement here. I'm saying, like, for these particular numbers.
But what I mean is, like, in that case, then it would be 4 and 2.
Yeah.
And then if I was following your calculations, then I think that would mean that in the case where you're told to chicken, it might be slightly preferable to dare. Or maybe I got it backwards.
Right. So I mean, so of course, like you could say, dare the outcome, the utilities here are minus infinity, right? And that would completely change the game.
Okay.
Yeah, I mean that's definitely not making a general statement here, just about these particular numbers that have that kind of cute interpretation. One point I should make is, like, in all of these interpretations of prisoners' dilemmas, chicken, and so on, when you map them into numbers, what's important is like the relation between different outcomes. So, for example, the fact that chicken is, so dare chicken is more preferred by one player but less preferred than the other to chicken, and then dare is the worst. So what you care about is the relation between these numbers. But what I'm saying here is only relevant to these exact numbers. So it's not a general statement about the game of chicken. I guess I don't want to say more right now because there's going to be a poll about it in a few minutes, but this is not a general statement. Yeah.
Why do we ignore the kind of recursive structure where the other player could ignore the equilibrium
Yeah, so remind me your name?
Ben.
Ben? Right, so Ben is asking, why do we ignore the recursive structures? I guess what you mean is, so player one could say, well, so player two is going to reason about what I'm going to do, and therefore, might want to deviate, and therefore I should be, take that into account and so on. So I think it's the same idea that also it's, you could ask the same question about Nash equilibrium as well. I mean, you could say, why am I assuming that player two is playing this strategy? He's going to reason about what I'll do, that I'll deviate, and then he'll deviate, and so on. So this is, it's just the basic, and it is an assumption, but it is the basic assumption underlying the idea of equilibrium, which is saying, assuming the other player behaves in a certain way, it is an assumption, then I'm better off behaving in the same way, and then, the same would hold for the other player. So you're right that you could say, and there are notions in game theory that look at this, look ahead with some horizon and so on, this more recursive structure. We'll also talk about it more explicitly when we talk about extensive form games next time. But, but for now, you can just think of it as an assumption. So we're basically assuming that players think that way. Alex.
So it's kind of, we can say that this assumption is saying that equilibrium is a local minimum.
Mm-hmm.
It's kind of when we have a lot of
Yes.
time, and like if we reason recursively, we can kind of jump to another.
Yes.
Yeah. Okay.
Yeah, excellent. That's a nice interpretation. Mm-hmm. Right. In particular, kind of one of the things that happens is what we saw in the prisoner's dilemma, where they could be stuck in defect, which is an equilibrium. If you did recursive reasoning, you could jump to cooperate, but like you said, it's like a local thing. Okay, excellent. So, so let me just make one point that I think is fun. So, we were sort of assuming this availability of a mediator. And, a lot of people, in particular cryptographers who are, really paranoid about this type of assumptions, would worry that, like, where would this trustworthy mediator, where would that come from? Like, why would both players trust that if I was told to play S1, player two was actually told to play, some strategy, that the mediator actually drew something from the joint distribution and told player two the right thing. So there is quite a bit of work, including in cryptography, about how to implement a mediator, and there are general possibility results that we can implement a trusted mediator. But I just wanted to give you this specific example where in the game we just talked about, we can actually implement the mediator with a hat. And here's the idea. So we're going to have this hat, and we'll have balls in the hat which are labeled with chicken or dare, with C or D. And then we're going to blindfold both of the players, and each one of them is going to pick one ball from the hat. I hope you guys can appreciate like this illustration that took me hours to make a few years ago. But this is what it looks like, and you can imagine like the two players each drawing a ball. Okay, so here's like the first poll question for today. Which balls should I put in the hat? Oh, sorry. Yeah.
So we pick a ball and then the first player put it back?
No, no, excellent. So yeah, the first player does not put the ball back in. Yes, good point. Okay, so which balls should we put initially in the hat in order to implement the distribution that we had in this slide? Okay. Excellent. Okay, so we have, interesting, it's like in a lot of my polls, there's like 68% for the right answer. I wonder if it's like the same 68% or different. Okay, but so the answer is 2 chicken and 1 dare, right? And I think this is reasonably intuitive. So for example, if we take the point of view of player 1, right? And again, imagine we have 2 chicken, 1 dare in the hat. So with probability 1/3, player 1 chooses dare. And then player 2 definitely chooses chicken. So this happens with probability 1/3. With probability 2/3, player 2 chooses one of the chicken balls. And then there are 2 balls remaining, chicken and dare. So that gives us these 2 outcomes with probability 1/3 each. Okay, great. So now I want to ask you a more interesting poll, I think. Poll number 2, and this is actually the last poll for today. What is the relation between correlated equilibrium and Nash equilibrium? So the first thing says every correlated equilibrium is a Nash equilibrium. The second thing says every Nash equilibrium is a correlated equilibrium. The third thing says, they're actually the same thing, but with confusing definitions. And the fourth thing says they're incomparable in the sense that there are correlated equilibria which are not Nash equilibria, and there are Nash equilibria which are not correlated equilibria. Okay, interesting. So now the opinions are a lot more mixed. There is a significant plurality for the right answer, which is Nash equilibrium implies correlated equilibrium. But quite a few of you also thought that correlated equilibrium implies Nash equilibrium. So let's first rule that out. Can somebody give an example of correlated equilibrium which is not a Nash equilibrium? We just saw it a few minutes ago. Yeah.
One physical 0, 1 third, 1 third.
Excellent. Right. So Ankush is saying, just think of the example we just talked about with the chicken game. So we said, the only Nash equilibria were chicken there, chicken, and half-half. And that thing with the 0, 1 third, 1 third, 1 third was not a Nash equilibrium. So this is an example of a correlated equilibrium, which is not a Nash equilibrium, and therefore it's not that the implication in this direction is not true. Now I claim that the implication in the other direction is true, that every Nash equilibrium is correlated a correlated equilibrium. So would anybody this is a bit tricky, but would anybody like to attempt giving an intuitive explanation for why this is true?
If you look at the definition for correlated equilibrium, we have the joint distribution.
Oh,
Isn't that similar to the way we define mixed? Like, one after the
oh,
other?
yeah,
The second one, when you say equality.
right.
Isn't that the same way when we define mixed?
Right.
equilibrium?
So let me ask a more concrete question. Let's say that I'm given a Nash equilibrium. How would I define it as a correlated equilibrium? Like, what would be the probability distribution P? Okay, so that would be like a concrete question here.
So for a finite set, there's definite finite set of actions possible. There always exists a Nash equilibrium, right? Possibly mixed.
Sure, yeah.
So why can't we just use that distribution as a joint distribution for P?
Okay, so what do you mean by using that distribution?
So you have some probability distribution for player 1 and player 2, which would be a mixed equilibrium.
Yes,
So we can compute a joint distribution based
Excellent.
on that.
excellent. So Ashwin is saying, so what the proposal is, given a Nash equilibrium, and existence is actually not crucial here because we're just saying for any Nash equilibrium, it's also a correlated equilibrium. But the construction is proposing is, we have a strategy, a mixed strategy for player 1, a mixed strategy for player 2. We can compute they're independent, but we can compute the mixed, the joint distribution over the two strategy spaces by just taking the product distribution of these two independent distributions. So the probability of playing this and this is the product of the two probabilities. So because things are independent. So that's the proposal for defining the correlated equilibrium. Now, intuitively, what's happening, is that if we look at this definition again, when player 1 is told to play some strategy by choosing from this joint strategy, because the two mixed strategies are independent, this tells them nothing about the strategy of the other player. Okay, so that's why the property of Nash equilibrium, that each strategy is a best response to the strategy of the other player, that means that this definition would apply, because essentially we have that property. Plus, because the two things are independent, when we get some advice, that tells us nothing about the strategy of the other player, and therefore we're just back in the Nash case and can use the property of each strategy as a best response in Nash to say that we have this best response strategy of correlated equilibrium. Okay? So essentially the idea is a Nash equilibrium has the additional assumption that the two strategies have to be independent. A correlated equilibrium could work like that. It could be independent, and then when I give one player advice, I'm not telling them anything about what the other player is doing. But it's stronger in the sense that I could correlate the two strategies, and then when I tell one player something about his strategy, it also gives them a hint about the strategy of the other player. Okay, so it gives me more tools in order to create equilibria. It's like a strictly stronger notion in terms of what I can do And it's like the set of correlated equilibria is larger than the set of Nash equilibria. Okay. Cool. So one nice thing about this is that, the fact that I give myself more power as the person trying to find an equilibrium is that it actually makes the computational problem easier than before. So before we said, finding a Nash equilibrium, we didn't talk about the details, but it's hard for this complexity class called PPAD. Here, the problem is actually easy, or polynomial time, and you can do it through a linear program. So let's see. We already did everything, but let's sort of write it down formally. So what we want to do is find the probability distribution P. So these are the variables, P of S1, S2 for every S1 and S2. Now, these two conditions are just the best response conditions that we defined for the two players. So all I did here is I copied this inequality over to the linear program. Okay, so this is a linear inequality on the variables P of S1, S2. So these are these two inequalities, just saying player 1 best response to player 2 best response to player 1. And then this is a joint probability distribution, so the sum of probabilities is 1, and all of the probabilities are in 0, 1. Okay? So we sort of already saw this before, but the only meaningful constraint here is actually a linear constraint on these variables P, S1, S2, so this is a linear program. Now, and again, why is this happening? Like we're saying, it's like a larger set, it's sort of a more complicated notion, but somehow it becomes easier. And the reason is that if you wanted to do something like this with the Nash equilibrium, you would need a variable for the probability of player 1 playing every action, and a variable for player 2 playing every action. But then if you want to say what's the probability that both things happen, that's a product of the two variables, and then you would lose the linearity of the program. Okay, so trying to do the same thing, but when you're forcing yourself to have independent distributions wouldn't work. And once you can have one variable for every pair, S1, S2, then it becomes a linear program. Okay? Yeah.
Why can't we have one variable for every pair in Nash equilibrium?
For every Nash equilibrium?
No. I mean, so the way we do this,
Mm-hmm.
I mean, why can't we do this in the case of Nash equilibrium? Can't we just introduce one variable for every possible pair in the joint distribution?
No, because that would, because then when you solve the LP and you're trying to find some solution, so it might tell you the probability of this pair is this, the probability of that pair is that, but that wouldn't lead to two independent distributions.
So are you saying that
so
given the joint distribution computing and given the fact that they're independent,
yes.
computing the individual distributions itself is a hard problem?
No, so what I'm saying is, you could, so if you wanted a Nash equilibrium, you could do the same problem, but add constraints that say the probability distribution P should be such that if we look at, the marginal distribution for player 1 and player 2, these two distributions are independent. But that's not a linear constraint either. Okay, so like one way to linearize, to like get away around this would be to say, I have separate variables, then you get a product. And I think your suggestion sort of, it makes sense, right? So you're saying we can still have this, but add additional constraints, but those constraints wouldn't be linear. Yeah, but that's a good point. Okay, good. So that took a bit longer than expected. I want to use the rest of the lecture to tell you about another, I think, very interesting concept. And this one, like I said, we'll also talk about very significant real-world applications and some stuff that you will be asked to implement in your homework. So to introduce this concept, let's look at another game. So it's this game. I don't want to tell you a story about this game. It's just like a bunch of numbers. But what I do want to do is solve this game using iterated elimination of dominated strategies. And like I mentioned last time, one of the problems in your homework, if you haven't done it yet, is showing that this leads to a unique Nash equilibrium if you can reduce the game to one strategy per player. So what would happen here is for the row player, up dominates down, so we can eliminate down. And then the column player just chooses between left and right, so they would eliminate right, and we would be left with up left as the unique Nash equilibrium in this game, even among mixed strategies. So, this is not that great because, for player 1, he's getting only 1, and there are 2 other outcomes where he gets 2 and 3, which is much better for him. Now, imagine that we changed the rules of the game a bit, and we actually allowed player 1 to make a commitment to which strategy he would play. So in the chicken game, one way to think about this is that I have the option to break the wheel, tear it out and wave it out the window, and that sort of tells the other player I have no way of swerving because I just broke the wheel, right? So this is a form of commitment to the strategy, there. And here, so let's say player 1 can sign some contract that says I'm committing to playing this strategy. And player 1, even though for him up dominates down, he's actually going to commit to playing down. So what happens if he commits to playing down? So now player 2 knows that player 1 will play down. So he chooses between a payoff of 0 and a payoff of 1. Of course, he prefers the 1, so he would respond by playing right. But then what happens, right? So then player 1 ends up getting 2 instead of getting 1 like before. So, basically player 1 committed to a strictly dominated strategy for him, but because of the way player 2 responded to that strategy, player 1 ended up with a better outcome for him. Okay, so we did change the rules of the game in allowing player 1 to make a commitment, but what this shows is that making commitment can actually improve your utility versus what you would get in a Nash equilibrium, like in this case in the unique Nash equilibrium. So player 1 was able to improve his payoff from 1 to 2. Now even nicer, if player 1 can commit to a mixed strategy, he can do even better. So imagine that player 1 is committing to playing down with probability 0.51 and playing up with probability 0.49. And now player 2 has to decide, the column player has to decide between left and right. So if he plays left, he gets 0.49. If he plays right, he gets 0.51. Right, so his best response, given this type of randomized commitment, is actually to respond by playing right. And then player 1 gets 3 with probability almost 1/2, and 2 with probability almost 1/2. So he's getting roughly 2.5, even better than before. And of course, you can make it like half plus epsilon, half minus epsilon. The assumption people usually make is that player 1 can just play half-half, and then player 2 will break the tie in favor of player 1. So, so this is really cool, right? So if we allow randomization, we can do even better. We can improve the payoff really significantly by committing in advance to some mixed strategy. So this type of game where one player can make a commitment and the other player best responds is called the Stackelberg game. And this type of strategy is called the Stackelberg mixed strategy, where player 1 commits to a strategy. And from the point of view of player 1, what he's trying to do, the leader, what he's trying to do is commit to a strategy such that when player 2 best responds, his own utility is maximized. That's sort of the optimization problem that player 1, the leader, is trying to solve. So in this game, the optimal solution for player 1 would be doing half-half and letting player 2 respond by playing right. Okay, so let's talk a bit about computing these Stackelberg strategies in games like that. So there's a nice paper in EC 2006 by Vince Konitzer, who was a PhD student here, and Thomas Sandholm was a professor here. And what they show is that in two-player normal form games, an optimal Stackelberg strategy can be found in polynomial time. So I'm going to show you this algorithm in the next slide, and we'll also ask you to implement it. However, if there are more than 2 players, then the problem is NP-hard. So I don't want to talk about this case because the applications we'll talk about have only 2 players. Okay, so I want to show you how we solve this in polynomial time for the case of 2 players. And again, it's going to be using linear programming. But this is it's a tricky, sort of a nice idea. Okay, a somewhat tricky idea. So here's what we're going to do. For each pure follower strategy, S2, we're trying to compute the strategy for player 1. So we're going to compute a strategy for player 1 using an LP. So the strategy will be X1. It's going to be a mixed strategy. And the LP will ensure that S2 is the best response for the follower. And that under this constraint, assuming that player 2 responds by playing S2, playing X1 is the optimal strategy for player 1. And then, so we're going to solve an LP like that, and we'll see what the LP is in a minute, for every possible S2. And then we're going to take, among all of these solutions, the one that gives the best utility to player 1. So before we talk about the LP, let's try to understand what's going on here. I mean, the problem is that, what you would want to do is just write one LP, like without this silliness of assuming that player 2 responds by playing something, So forget about that. Let's just write a program that says, okay, the variable will be the strategy of player 2, and then we'll have some constraints about the utility and so on. The problem is that it would be hard to sort of capture how player 2 best responds to player 1 in a program like that, where we don't constrain what player 2 is doing. So what this is trying to do is say, okay, we're going to fix the response of player 2 in advance. So we know what player 2 is playing, and then in our LP, we'll make sure that this is indeed the best response, and subject to that constraint, we'll optimize the utility of player 1. So graphically, the way it looks like is, so without going too much into details, you can think about, maybe this is the strategy space of player 1. It's the space of all probability distributions that player 1 can play. And then, let's say there are two possible actions or strategies for player 2. So maybe there are two regions in the space. This is the region where player 2 responds by playing strategy 1. And this is the region where player 2 responds by playing strategy 2. Let's call them up and down. Or left and right. Okay, so this is left and this is right. And what we're saying is, in each one of these regions, we're going to choose the best thing for player 1. Okay, so let's say, like in this region, the optimal strategy is this vertex. In this region, the optimal strategy is this vertex. And then we'll ask, and now we've covered the whole space, and we'll ask which one of these gives me the best outcome, and that's what I'll go with. Okay? So again, like we're looking at a partition of the space, of the strategy space of player 1, a partition of the space. We're optimizing inside each region, and then we're taking the best overall. That's the high-level idea. So how do we write this LP? It's pretty simple. Yeah.
Can you explain again why it's hard to just write one LP?
Yes. So let's look at this LP, and then we'll go back to the question. Okay. So you'll see that in this LP we use the fact that we know what player 2 is doing, and then you can try to think about how you would write this LP. You can't if we sort of don't know this in advance. Okay. So let's look at the LP. So what do we have here? We're saying our variables are these variables x1 of S1, which is the probability player 1 plays the strategy S1. So we want to maximize the expected payoff of player 1. So this is the expected payoff. The probability plays S1 times the utility when he plays S1 and player 2 plays S2 for the fixed strategy S2. Okay, so keep that in mind. Now this constraint is saying playing this mixed strategy X1 is, playing S2 is the best response to X1. So when we look at the utility to player 2, player 2's expected utility when playing S2 is at least as expected utility when playing S2 prime for every possible S2 prime. So this is the best response constraint. And then this just says this is a probability distribution and all of the probabilities are in 0, 1. So it's just going back to Alex's question. The problem is how would you write this thing? So now you're just able to write utility for S1, S2, but now you have to write the utility of S1 given the best response to S2, and you somehow have to fit like what, it's not going to be a linear program. Okay, or at least I don't see like a natural way. This seems like a much more natural way of writing this kind of thing as a linear program. Ashwin?
Why is this LP guaranteed to have a solution?
So this LP, right, so it could be the case that some of these regions are empty, and then it will have no solution. I mean, that's fine. But for any, but what we're doing is we're partitioning the space into regions where the best response is some fixed strategy of player 2. Now, some of these regions will be non-empty because this is a partition of the space.
So the theorem says that if it exists, we can find it in polytime, but it doesn't say that it
Uh,
always should exist.
No, so the theorem says, there always is an optimal strategy. So this is just saying you just want to maximize your utility.
That means this LP must have a solution, right?
So-
By the theorem.
Okay, I mean, it's a really good point. So not each one of these LPs can have a solution because it could be, so for example, if player 2 has a strategy which is strictly dominated by another strategy, it's never going to be a best response for him to play that strategy. And then the LP, when you take S2 to be that strategy, will be infeasible. I mean, that's fine. But what I'm saying is still, so you could have some region which is empty, like it's not in this picture at all. But what I'm saying is, nevertheless, in this space, there's some strategy which is optimal. And because we're looking at a partition of the space, we're basically looking at all possible strategies for player 1. So, fine, some regions could be empty. I mean, that's fine. But the regions that are non-empty are going to cover the entire space. And then when I optimize inside each one and take the best among all of the regions, that will give me the optimal solution.
But the utility would never be achieved, right? Because player 2 wouldn't go for that best response because he has other strategy which is dominant.
So think about it that way. In the dominated case, yeah, sure.
Yeah.
So we would go for a best response in a different region. I mean, that's fine. So, we would just have some empty region, and we would say, I mean, what you're saying is, I'll give you two ways to think about it. So one, directly for your question, what we're saying is we take the best solution among all of these, but all of these that had a feasible LP. If the LP is infeasible, we say, okay, we don't want to play a strategy such that the best response is that strategy. I mean, it can't happen. But think about it this way. So in this space, there's some point which is the optimal strategy, right? And let's say it's this point. And this point is inside this region. So now when you take it's actually going to be on the vertex of the region, but never mind. So now when you take the optimal strategy in this region, it should be able to find this point, right? So that's basically why we'll find the globally optimal solution. It's contained in one of these regions, right? And in this, if the response here is right, or let's say middle, then it is the case that when you play your optimal strategy, player 2 responds by playing middle. Right? So now when you optimize over this region under the assumption that player 2 responds by playing middle, you will be able to find this point or something at least as good.
So the strategy for the other player is fixed. Is that?
So it's not fixed. It depends on what you're playing. Okay, I mean, this is very confusing. So it does depend on what you're playing, but we're saying, in this region, for all of the points in this region, the best response of player 2 will be L. And for all of the points in this region, the best response for player 2 will be M. Okay, so then, so when we're adding the constraint that says the best response has to be M, for example, it's basically going to be these constraints.
So you're saying that the utility that player 1 would get, that may not be the best that player 1 can get because player 2 can have a dominated strategy, but given that player 2 plays that strategy, whatever response that
Yes.
you will get, utility will get will be the best. for
Exactly. So right, so it could be it could be the case that you look at this region, and maybe the optimal point in this region is this one. It could be a suboptimal, so assuming that player 2 plays right, this is the optimal thing for player 1 to do, but player 1 could play a different strategy here and get a better outcome. So, right, so that's why we're saying, inside each region, the strategy of player 2 is fixed, and we'll take the best overall. Okay. Priya?
Are we making the assumption that player 2 is playing a pure strategy, or is there something about the way that we're implementing the first constraint that sort of actually makes that the best?
Yeah, that's an important point. So I should say this explicitly because it really is an important point. So in an equilibrium, it's also true in a Nash equilibrium, a best response can always be a pure strategy. And moreover, every strategy in the support of an equilibrium strategy, every pure strategy in the support of a mixed equilibrium strategy is itself a best response. And the reason is that your utility for a mixed strategy, if you fix the strategy of the other player, is a convex combination of your utility for every pure strategy in the support. So if one of them had a strictly lower strategy, you just wouldn't use it. Okay, so that's why we can assume that player 2 responds by playing a pure strategy, because there's always one that is optimal for him. Okay, great. Okay, so hopefully, are there any other questions about this algorithm?
Can you briefly, like, say that? So you said, like, if you consider the whole region, there is some optima. Why is that true?
Because it's because these regions are polytopes.
No, not in like the whole region. When you take the whole region and you said that there is like a global optima there.
Yeah. You're saying just like in terms of we could have some things that sort of converge to an equilibrium, but not.
Yeah.
I mean, it's just like the usual, compactness. It's just the way everything.
No, that one. Like how to formulate? Like it could be cycler. Like why we cannot have a cycle of dominated strategies. Something like if player 1 plays this, then player 2 will change to that, and if player 2 fixes that, player 1 will change to that, and it's like cycles, and you do not have the option.
So you agree that every point in the space, every strategy, which is a point in the space, has some fixed best response for player 2. Right?
Yes.
Right? So that's why you avoid like this kind of cyclic thing. I mean, it's really like the space is really partitioned into these regions. For every point, like you can say in advance, if I play this strategy, player 2 will respond in this way. Like this would optimize, of course, under some tie-breaking assumptions. Okay. Cool. Okay, so if you thought that was tricky, things are going to get even trickier. Yeah, I'm actually deliberating whether. So I've added a few slides where I was like, I'm going to really challenge you guys, but first of all, like we don't have a lot of time. So let's see, let's continue talking and we'll see like if we get to like the really tricky slides. Okay, so I want to tell you about a particular application to security games, and it's like an incredibly exciting application. It's had a huge real world impact, and it's just an implementation of this idea of Stackelberg games in the real world. So this is something that's actually algorithms based on these ideas are deployed by major security agencies, airport security at LAX, the Federal Air Marshal Service, the US Coast Guard in several different applications, guarding harbors, guarding ferries. So they have several different algorithms that they use, all based on these ideas. These ideas are now being extended to wildlife protection and cybersecurity and many other things with really amazing implementations. So here's the basic idea behind this. The idea is to think of these situations as a Stackelberg game between two players, a defender and an attacker. So the defender has security resources. In the case of something like LAX, it can be patrols, cameras, and so on. And the attacker could be a terrorist or a drug dealer or a smuggler. So they observe the strategy of the defender. They see how the defender deploys the resources, and then they best respond. Okay. So we can think of this as Stackelberg game because the leader, who is the defender in this case, chooses some strategy. The follower, the attacker, gets to see that strategy and then chooses the thing that will be best for them. And again, what the leader, the defender, is trying to do is optimize their own utility, assuming that the follower will actually be able to surveil their strategy and respond to it. So that's sort of how we fit these situations into the Stackelberg scenario. So let's talk about a specific formalism that's been very popular for thinking about security games. And then later on, I'll tell you more about like the gaps in the simple model and what people have been doing in AI to address them. Okay, so here's a concrete model for this type of setting. We have a set of targets that we denote by capital T, and the targets themselves are 1 to n. So these are the targets that the defender is trying to protect. So you can think of airport terminals in the case of the LAX airport police. You can think of ferries if it's the Coast Guard and so on. If it's the Federal Air Marshal Service, it's flights. And then the defender has a set of M security resources, which we denote by omega, that are available to them in order to protect the targets. So in the picture, the resources are the squares and the targets are the circles. Now we also have a set of schedules which are subsets of targets. So the idea in a schedule, like if a schedule contains these three targets, the idea is that I can protect these three targets simultaneously. And then a resource omega can be assigned to one of the schedules in the set A omega. So this illustration shows an example. So these three targets are in one schedule, and these four targets are in another schedule. And then this resource can either be used to protect these targets or to protect this schedule, which is these four targets. And this resource can be used to protect these four or these three. So this A omega would just be the edges in this graph. So it tells you to which schedules can I assign a resource. Now, an attacker, the attacker's strategy space is choosing one target to attack. So, to recap, the defender is going to choose a deployment of the resources to schedules. That's a pure defender strategy. The attacker is going to respond by choosing one target to attack. Yeah, Jonathan.
Is there a limit on how many targets can be in a schedule? I guess why can't you just have one schedule that includes all of the targets?
So it's just a matter of how the game is defined. You're trying to capture a real-world situation. So think, for example, of like a camera. So it can either point in this direction and protect these targets, or in this direction and protect these targets, but you can't monitor everything at the same time. So you could define a game where there's like a schedule that contains everything and can be protected. That would be like a very easy game. And in a game where the defender has no shortage of resources. But usually the defenders do have a shortage and have to prioritize where to allocate the resources. Okay, so let's define the utilities in this game. So for each target T, there are four numbers that define the utilities of the two players. So U D plus of T is the utility to the defender if target T was attacked and it was covered. So D is the defender, plus means covered. UD minus of T is the utility to the defender when target T was attacked but wasn't covered, wasn't protected at the time. And we're assuming that the defender would rather have the target protected than not protected. And similarly for the attacker, we have the same thing, but the inequality is in the other direction. The attacker wants the target not to be protected when it's attacked. Now, like I said, a pure strategy for the defender is a deployment of an assignment of the resources to schedules. And a mixed strategy is a probability distribution over these pure strategies, as usual. Now, the point is that when you have a mixed strategy, it induces a vector of coverage probabilities that tells you what's the probability that each target is covered. So C1 is the probability that target 1 is covered, C2 the probability of target 2, and so on. So notice that a randomized strategy induces a vector C like that. So you can sort of think of the strategy space of player 1, of the defender, as vectors of coverage probability distributions. Now, the utility to the defender and the attacker depend on the probability that the target is covered, depend on which target was attacked, and depend on the utilities. And the definition is pretty simple. So the utility to the defender when target T is attacked and the vector of coverage probabilities is C, the only thing that matters is what's the probability the target T specifically was protected. So it's a probability the target T was protected, which is CT, times the utility to the defender when it's protected, plus the probability that it wasn't protected times the utility to the defender when it wasn't protected. All this is the utility to the defender. And we can define the utility to the attacker in the same way by replacing D with A. Ashwin?
Do we not account for probability that it's not protected if the attacker attacks?
Yeah, so you first look at which target was attacked. right? And then the probabilities depend on, I mean, the utilities depend on which target was actually attacked. Okay, so is everybody okay with this formalism? Okay, so here's a question to you guys. This is a two-player Stackelberg games, right? And we said before, there's a result by Konitzer and Sandholm that says in every two-player Stackelberg game, we can compute an optimal Stackelberg strategy in polynomial time. So does that mean that we can actually solve this game that we just defined in polynomial time? Okay. Hence, the answer is no. So the question is, why not? So let's think about, yeah, class. Excellent. So polynomial in the representation of the game. Fantastic. Okay, so class is saying, okay, what's the problem? So suppose that okay, I mean, there is actually, I mean, this example, you could actually argue a bit about it, because so what class is suggesting is the strategies are going to be subsets. You could cover any subset of the targets. So a subtlety with this kind of thing is that to explicitly represent that, you'd have to give all possible schedules, like all of these subsets, and then the representation would be very large as well. But the idea is completely correct. I mean, you could say something like that concisely. But let's say that we do have to, I mean, the schedules are part of the representation. But suppose that, let me give a slightly different example. Suppose that the schedules are singletons, so every resource can only cover one target. And then the situation we have is, let's say, you know, resource number 1 can either cover target 1 or target 2. Resource 2 can cover target 3 or target 4, and so on. Right, so here there aren't that many possible schedules. It's just singletons. But the strategy space of the defender, what is it? So for each one of these resources, I have to decide, should I use it to cover this target or this target? This one, should I use it to cover this one or this one? And so on. So if I have n targets, I'm going to have like 2 to the n over 2 possible assignments of resources to targets in this example. Okay, so this is an example where even if I said the size of the game depends on like the set of all schedules, there, you know, the number, the size of the strategy space of the defender is exponential in the representation of the game. It's very large. And therefore, you know, when we think about that, that approach that we talked about to solve the game in polynomial time, remember that what we had, right, what we have here is we have a variable for every pure strategy of the leader. So when you have an exponential size strategy space, this LP is going to be very, very large. It's going to have an exponential number of variables. So this is, I mean, this whole thing is sort of a complexity theoretic subtlety, but it's making an important point, which is it's really difficult to solve these games in practice. And the reason why it's difficult is because the strategy space of the leader is so large. Okay, so there is a lot of work on how to solve you know, these games in practice, because there are these deployed applications that have pretty large games, and it is a very, very big problem in practice to actually solve them. Okay, so I'm going to skip the super challenging slides, which are these ones. I'll remove them from the slide deck later. So let me just spend like the last 10 minutes sort of talking about, you know, giving you like a broader AI viewpoint on this agenda of security games and the type of research people are doing in order to make this a reality. So like I said, I mean, the impact this has had is large. This line of work was initiated by a group at USC led by Professor Milan Tambe. He's been working on this for like 11, 12 years now. And I think a lot of the credit goes to him in terms of actually convincing these major security organizations to deploy these algorithms. But I think, I mean, so I think this is really amazing. But there are many, many issues. And I think one of them is that it's often unclear to decision makers what's actually going on. Like why, I mean, game theory sounds cool and everything, but what actually is giving the benefit in practice? So this is just one example that I like. It's from a news article in Newsweek that came out when the first application was deployed. And the text is very small, but let me read to you like one part of it. So it says that this was when it was deployed in the LA International Airport. And it says, now all airport security officials have to do is press a button labeled randomize, and they can throw a digital cloak of invisibility over where they place the cops' anti-terror checkpoints on any given day. So this is really emphasizing the randomness part of it, right? We have a mixed strategy for the defender. That would be the optimal Stackelberg strategy. And it's sort of saying, oh, the beauty here is that we're automating the randomness. But of course, that's very simple. So you don't need like all of this game theoretic machinery and working very hard to solve the Stackelberg game just to randomize. That's really not what's giving you the benefit, or at least like not a big part of the model. So, the fact is that there are quite a few gaps between the game theoretic model and reality. And what's been happening is like even the basic model has worked really well. But it's sort of, one could wonder like which part of the model is the one that's giving the benefit. Like is it, because of these gaps that we'll talk about, like is it the randomness, is it actually the game theory? And I think like a lot of the research that's been done in the last decade tries to aim at like narrowing down these gaps and really trying to get a very accurate representation of reality and getting even better results in practice. So here are some of the gaps that exist between the basic model and reality. So one thing we sort of assumed is that the defender knows the utility function of the attacker. Right? So in a Stackelberg game, when the leader optimizes their own strategy, they're asking themselves, how would the follower respond if I play this strategy? But this requires knowing the utility function of the attacker. Now, in real life, if we're thinking about a terrorist or a drug dealer, there are risk analysts whose job it is to come up with numbers like this. But of course, that's not going to be accurate. So you're not going to have an accurate representation of the utility function of the attacker. And then when you compute the best response, it's going to be with respect to the wrong utility function. So one solution people have been looking at, especially in recent years, is machine learning, of course. And there are two flavors to this. One is looking at historical data, where we know how the defender is played. And in some cases, like wildlife protection, there's a lot of historical data. Like, in those cases, we're trying to fight poachers. And there are ranger patrols that keep track of where poachers were detected, so you can find like signs of human activity. So they have a lot of data over many years, and you can use learning in order to learn something about what the poachers care about, which conditions they care about. Another approach is online, so basically modifying the strategy of the defender to learn about the utility function of the attacker online. So part of what we would be trying to do is play strategies such that when the attacker responds, that teaches us something about their utility function. So there's quite a bit of work taking that approach as well. So that's one sort of big gap in how people are addressing it. Another big gap is that in a Stackelberg game, we're assuming that the attacker will know exactly the defender's strategy and best respond to it. In security games, the way people think about this is the attacker has surveillance, and they're sort of taking samples, they're observing what happens, and over time they get a really good picture of what the defender is doing. But of course, this would require an infinite amount of time and like a really, really diligent attacker. So what happens if the attacker doesn't have a perfect idea of what the defender is doing? So one approach people have taken to reasoning about this is thinking of the attacker as a Markov decision process. It's something we haven't talked about, but it will come up in the last 3 lectures of the course when we talk about AI in education. So we sort of try to take the point of view of the attacker and think about when will they stop taking samples or when will they continue taking samples? And that gives us some idea of how much information we expect the attacker to gather. And that informs how we compute our strategy. So that's one approach, but there's some other work that basically says this is not a major problem, in the sense that even if you assume that the attacker has perfect information, even if they don't, you're not actually going to lose a lot from that. So as long as they have like sufficiently many samples, it's pretty safe to assume that they have perfect information. And the third gap is that, again, like in Stuckelberg games, we assume that the attacker is perfectly rational in the sense that they choose the best response. Okay, and this is sort of orthogonal to the other stuff we talked about. So we said, okay, we don't know the utility function and so on, but even if we knew the utility function, and even if they knew exactly our strategy, maybe they don't have this power to optimize their strategy, or they're not smart enough to just optimize their strategy given this information. So this is another issue. And to address this, people have talked about many models of bounded rationality, which is something that has been explored in depth in game theory and behavioral economics. So thinking about how to reason about players that don't play optimally. So for example, there are models that basically say the attacker or the follower will have some probability distribution where its mode is going to be the best response. And then as you get less optimal, the probability decreases, but there still is some probability. And different models differ in like how this probability decreases. So this is something people have looked at in depth. And for example, some groups have run human subject experiments like this one. So this is in the wildlife protection domain. And essentially what they're doing here is saying, like you want to protect these sheep, and the attacker is trying to poach like as many sheep as possible. So now the human is taking the point of view of the attacker, and what you're being shown is this heat map is the probability that every space in the grid, every square in the grid is covered. These squares are the targets in this case. The utility to the attacker depends on how many sheep there are in the square, but also, of course, on whether it's covered or not covered. So these are the probabilities. And then the human subjects, who are taking the point of view of the attacker, have to choose which square they would attack. Okay, and then you can see like how well these responses actually fit these models of bounded rationality. Okay, so people have come up with many different models and have run experiments like this to see which models are the best. So this is a sort of a very high-level overview of a decade of research on security games, but the short summary is there are very big gaps. Like even in the initially deployed algorithms, there were very big gaps between theory and reality. Nevertheless, these algorithms have worked really well. So they've worked better in very realistic tests that these organizations have done compared to what they used to do. And then over the last decade, people have been working on narrowing these gaps and getting better and better representations of reality that lead to better security. Any last questions? Okay, see you guys on Wednesday.